Chapter 4. Another tool of science. Hypothesis testing. Quote, "The great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact." Thomas Huxley. Hypothesis testing is one of the most widespread tools of science. Its goal is to determine whether a hypothesis is correct. As Thomas Huxley's 1825 to 1895 aptly put it, the pursuit of facts matters most in science, regardless of how beautiful or appealing a hypothesis might be. If this was a technical book, I would dive deeply into the complexities of hypothesis testing. While the technical details of this scientific tool are numerous and complex and require a foundation in probability and statistics, the essence of hypothesis testing is quite simple. In this chapter, I will briefly introduce hypothesis testing without technical jargon, and then discuss how this tool can be misused or abused. Hypothesis testing is a structured statistical technique that starts with formulating a hypothesis, continues with data collection, and ends with analyzing the data and conclusions. Let us walk through these 3 steps using an example. My wife is much better than me at doing more than one task at a time. This has gotten me thinking about whether this has anything to do with our different biological sexes. I am male and she's female. This little story is not a hypothesis, but a hypothesis in the making. A hypothesis in the making consists of our observation and our best guess at what a fact could be. To transform this into a hypothesis, we must formulate it. Formulation of a hypothesis involves the application of modeling and measurement. We must first model what we are interested in and then specify how to measure the model. In this case, our model is the human capability to multitask. Once we have our model, we must determine how to measure it. For the measurement device, we can accept an individual score in a specific game requiring multitasking as a measure of multitasking capability. Now that we have a model and measurement device, we can formulate the hypothesis. In this example, we hypothesize females score better than males in multitasking game. Pay attention to the fact that behind this short sentence, as the hypothesis, there are many moving parts, such as the model and the measurement device. If you have ever played a multitasking game, try this one on congregate.com website. Here's the link: https://congregate.com/games/iclime/multitask. I scored 57 on my second attempt at playing the game. I counted the first attempt as my getting to know the game and the second as measuring my multitasking capability. Give it a try and see how you do it. Now that we have the hypothesis, models, and measurement, let us discuss the data collection. If we want to know without a doubt if our hypothesis is confirmed, we would have to collect data from all female and male individuals worldwide, which is too big, too ambitious, and most importantly, unnecessary. The need for the result must be more critical to justify such an expensive data collection. Instead of discarding the hypothesis, we adjust our approach to certainty. Instead of seeking absolute certainty, we settle for 95% confidence in our results. The concept of confidence is a complex statistical idea. So if you are not familiar with statistics, you can take it at face value. When we say we are 95% confident, we are 95% sure about the result. By settling for 95% confidence instead of 100%, we do not need to collect data from the entire population. Using another essential statistical tool, random sampling, we can significantly reduce number of individuals from whom we need to collect data. Assuming a global population of 7 billion, The number of samples required for 95% confidence is 385. When you think about it, this is a good compromise. We let go of complete certainty and settle for good enough confidence, 95%. But we reduce our data collection costs from $7 billion to $385, assuming each sample costs $1. Pay close attention to the fact that the 385 individuals cannot be just any of the 385 individuals we happen to come across. We must collect the data through random sampling to ensure that the 385 individuals will give us 95% confidence in our results. Random sampling is easy to understand. You randomly choose a subset of the population for data collection. Nevertheless, it takes more work to implement. Let us review the following 3 data collection scenarios. While you listen, consider whether they describe random sampling. One morning, I woke up, drove to every Starbucks store around me, walked up to everyone sitting, and asked them if they were willing to play a game that would take up to 5 minutes in exchange for $1. I was able to collect data from 385 individuals in 3 days. The cost of data collection would be $385 plus $600, totaling $985. The $600 costs an individual 3 days of work. The $600 is what we would have to pay an individual to work for 8 hours for 3 days at a $25 an hour rate. I created a LinkedIn post and asked my connections to play the game and report the results. Once the numbers of participants reached 385, I removed my post. The cost of data collection for this method would be very close to zero. I partnered with Starbucks and we randomly chose 385 stores worldwide. For each store, we randomly generated a time and a date within a year that the store would be open. And we instructed the store's baristas to get the first customer who walked into the store on or after the generated time and date to play the game. On average, it only took a free coffee for customers to accept playing the game. So the cost of this data collection for Starbucks would be around 5 multiplied $385, totaling $1,925. I cannot imagine why Starbucks would ever agree to help me with such an experiment, but we're just imagining here. So, which of the previous 3 data collections would manage to collect the data we need randomly? The answer is neither. Let us go over them one by one. The first one is not random at all. The only individuals who would have a chance to participate in the data collection will be the ones who live nearby and like sitting and working in Starbucks. The population of the city I live in is 70,000, which tells me 99.999% of the population does not have a chance to be part of this study. The idea behind random sampling is that everyone in the population has at least the same chance of being selected. Even if I were okay with changing my hypothesis to, in my city, females score better than males in the multitasking game, the data collection was still not random sampling. Do people who don't go to Starbucks have a chance of being selected? The second data collection is not random sampling either. We need to answer whether everyone has the same chance of seeing and reaching to my LinkedIn post while it's still up. Of course, the answer is no. Even if I settled for among my LinkedIn connections, females score better than males in the multitasking game, the data collection does not provide a random sampling. Did all of my LinkedIn connections have the same chance of seeing and reacting to my post? What about the connections that rarely go on the platform? The third data collection is the closest to random sampling, but only for the following hypothesis. Among Starbucks customers worldwide, females score better than males in multitasking game. Pay close attention that it is not truly random sampling because Starbucks customers who go to Starbucks more frequently would have a higher chance of being selected. Honestly, truly random sampling would be costly too. Maybe not as expensive as complete data collection, but still very expensive. In most experimentations that attempt to use random sampling to reach 95% confidence level, the scientists will do their best within their budget to approach a good enough random sampling. For instance, if I were the blind peer reviewer of an academic paper that described the third data collection, I would accept it. Before analyzing the collected data in hypothesis testing, let me share with you that the collection part of hypothesis testing is where most things go sideways. So, if you want to critically examine the results of a scientific effort that has used hypothesis testing, you might focus on the data collection. If you trust the integrity of authors, which in most cases you should not, it can suffice to rely on their description of the data collection. Bringing in the next level of scrutiny is not that difficult. Just imagine that you would be the one doing the data collection and how much it would cost you. See if the experimenters could have afforded the data collections they are proposing. And if so, who funded it and why they decided to spend that kind of money. Once the data is collected, the analysis part takes place. We will examine the data in this part to see if it supports our hypothesis. For instance, in the multitasking example we have been discussing, we compared the average performance of males and females in the sample. Let us say the average performance of female is 57.2 and the average performance of males is 57.3. We can see that males in the samples perform better than females in the sample by 0.1. So, do we conclude that the data does not support our hypothesis and that males are better at multitasking? The answer is no. Why? We must remember that what we have collected is the average of the sample, not the population. As we do not have perfect information, we need to be cautious. Statistically speaking, the difference between the two averages must be significant enough to conclude that the collected data does not support our hypothesis. What is significant enough? It is calculated by the probability of the sample happening if our hypothesis is correct. For instance, the probability of these two averages happening in a population where females are better at multitasking game than males would be 0.35 or 35%. This probability is not low enough, so we cannot reject the hypothesis. If this sounds odd, let us do a quick experiment together that will help you understand how this probability value does not indicate enough significance. All you need is a coin. So, we hypothesize that the coin is fair, or in other words, the probability of getting heads and getting tails is equal to 0.5 or 50%. Now, before continuing to listen, go ahead and toss your coin 16 times and record how many times you've had heads or tails. The following table shows all the possible outcomes that your data collection might have. This table shows two columns, numbers of heads and numbers of tails. I will just read each row. 16, 0, 15, 1, 14, 2, 13, 3, 12, 4, 11, 5, 10, 6, 9, 7, 8, 8, 7, 9, 6, 10, 5, 11, 4, 12, 3, 13, 2, 14, 1, 15, 0, 16. You may also see the table at the following link, royjafari.us/books/the-dividing-edge-of-science. After collecting your data, tossing your coins 16 times, indicate in the preceding table which of the listed possible outcomes happen for you and your coin. Now, think about your conclusion based on your data collection. Would you walk away thinking your coin is fair or unfair? When I did the experiment, I got 6 heads and 10 tails. Even though I got 4 more tails than 6 heads, I would walk away thinking I did not have enough evidence to believe the coin was biased. But how? That is where the probability of the sample happening comes into the picture. The following table shows the probability of the possible outcomes if the hypothesis that the coin is fair is correct. This is a table with 3 columns. Columns header are number of heads, number of tails, and probabilities. I will read each row. 16, 0, 0.000015. 15.1.0000244, 14.2.001831, 13.3.008545, 12.4.0277771, 11.5.06665, 10.6.122192, 97.174561, 88.196381, 79.174561, 610.122192, 511.06665, 412.027771, 313.008545, 214.001831, 115.000244, 016.000015. You may also see the table at the following link: royjafari.us/books/the-dividing-edge-of-science. Looking at the preceding table, the most likely outcome when a coin is fair has about 20% likelihood. This means that out of all you listeners who are listening to this book and did this experiment, only 20% of you must have arrived at eight equal numbers of tails and heads. This claim is correct if all of you have used fair coins, which should be the case. At this point, you must agree that it would be unreasonable if we decided to label any coin that got anything but 8 heads tails as biased in this experiment. However, if you end up with outcomes with probability less than 5%, that is 0.05, then the chance of that outcome is small enough for us to raise our eyebrows and be suspicious of the coin. So if you got any of the following: 11.5, 10.6, 9.7, 8.8, 7.9, 6.10, and 5.11, you must walk away thinking the experiment did not show you enough evidence to reject the null hypothesis. Based on the preceding table, if we were to judge 100 fair coins with the described data collection, we would judge between 7 to 8 of the 100 fair coins by mistake. This is the compromise we accept because we settled for not doing the data collection with more tosses. After this quick coin tossing digression, let us return to our multitasking game. We got a sample in which the male average was higher than the female average by 0.1. Since the chance of this outcome happening is 0.35 or 35% greater than 0.05, we will walk away from this experiment thinking we cannot reject our hypothesis. Does this mean we have proven that females perform better in multitasking games than males? Not at all. Our data showed no significant difference between male and female scores. Given our hypothesis, we would have said there was a significant difference between males and females in our sample only when the probability of the sample happening was very low, smaller than 0.05 or very high, larger than 0.95. This chapter becomes a bit too technical. So here's a list of bullet points you should take away from it. Before hypothesis testing is possible, we must model what we want to study and decide on our measurement device. In this study, our model was the multitasking capacity of individuals, and the measurement was the individual's score on multitasking. Right off the bat, important decisions need to be made, and these decisions can dramatically change the course of the study. Data collection is the most crucial part of hypothesis testing after modeling and measuring. If the data collection is not done correctly, intentionally or unintentionally, the result of the hypothesis testing should not be trusted. Hypothesis testing uses random sampling, and ensuring you have a random sample is a tricky business. Read the description of a study's data collection and ask yourself the following questions. Have all the individuals in the study's described population had an equal chance of being chosen for the sample? If the answer is no, then the data collection is not a random sampling and the study must not be trusted. If the data collection sounds reasonably random, could the author have been able to afford the described data collection? If not, the study cannot be trusted. If the data collection sounds reasonably random, and if the authors could have afforded it, why did they decide to spend that much on it? If their intention is self-serving, that casts doubts on the results presented in the study. Examples of self-serving funding reasons are abundant. For example, a company that produces shampoo would like to be able to advertise that through clinical experiments, hypothesis testing, the shampoo invigorates your hair. First and foremost, we must ask what the model and measurement for such a clinical study is. Does it sound logical to have the following model? Hair invigoration. Second, how on earth can they measure hair invigoration? In my daily life, I would stop here and not give this advertisement another thought. But for the sake of practice, let us continue. Third, what is their description of the data collection? Does it sound like random sampling? Even if it does sound like random sampling, a fourth question is, why did they do this study? The answer is to be able to advertise. Their shampoo is proven clinically to invigorate your hair. Are they lying when they tell you this? Not literally, because they probably do have a scientific journal in a peer-reviewed journal that describes the hypothesis testing that leads them to believe the formula they're using in their shampoo is both safe and increases the hair's invigoration. However, I would bet that they are lying to you figuratively, as there are various ways they can get a scientific-looking paper in a peer-reviewed journal just to put forth their claim. If you're not familiar with what peer-reviewed scientific journal articles are, do not worry. Chapter 6 is dedicated to peer-reviewed scientific journals. In the next chapter, we will discuss correlation versus causation.